So we're going to look at today, we call the fundamental theorem of algebra. And what this says is a degree n polynomial, some like third degree polynomial, fourth degree polynomial, fifth degree polynomial, degree n polynomial has exactly n zeros and n linear factors. Now, it doesn't say that there are exactly n x factors. So you have, x intercepts. If you have, let's say, x minus c, that's a factor. There's a factor there. All right. Then x equals c is a 0. And then c comma 0 is an x-intercept if c is real. If c is not real, then you don't have these x-intercepts. And so we've been talking about up to this point about real numbers. So we've had all three connected. Now we're seeing you can have the first two for some numbers, but not an x-intercept because it might not be a real number. It might be a complex number with an imaginary part. So, but this is going to help us. This connection for real numbers is going to help us to deal with other types of problems. And so I kind of want to go over some basic stuff that either we have talked about before or we haven't maybe talked about directly, but we have run across it, and you may have noticed it before. So let's say we were asked find the x-intercepts of the following function: f of x equals 6x squared minus x minus 35. Okay, so we're going to set this equal to 0, and we're going to solve it. And so let's say I'm going to say 6 times 35. What's that? That's 210, is that right? 6 times 35, that's 210. All right, so what are the factors of 210 that are different by 1? So they have to be very close to each other. Half of the factors, the integer factors of 210, or I should say whole number factors of 210, are less than the root of 210, square root of 210, and half are more than that. So square root of 10 is 14 something. So let's see, does 14 go into 210? So yes, 14 and 15. Those are different by 1. I want it to be a negative, so negative 15, positive 14. I'm going to do this, I'm going to factor this by grouping here. So positive 14x, negative 15x. What I've just figured out here is what were the O and the I when you FOIL. And now I'm just ripping them back apart here. So first two, they have a 2x in common. Take that out, you get a 3x plus 7. And so whenever you do grouping, you have to get the same exact parenthesis here, 3x plus 7, which means negative 15x divided by positive 3x means this has to be a negative 5. Let's see, negative 5 times 3, negative 15, negative 5 is negative 35. Okay, so that works. Common factor is 3x plus 7, and then you get 2x minus 5 as the other factor. Set each of these equal to 0. So these are the factors again. 3x plus 7 equals 0. 2x minus 5 equals 0. Subtract 7. 3x equals -7. Divide by 3. Add 5. 2x equals 5. Divide by 2. Those are the zeros. And so -7/3, comma 0, and 5/2, comma 0 are the x-intercepts. And again, when we're talking about real numbers, these are all connected to each other. These zeros, factors, x-intercepts. What I want to point out here, why I want to do this example, besides just to remind us of that connection, is if I look at these zeros here, and I look at the denominators, 3 and 2, 3 and 3, 2 and 3, and I look back at the original problem. What I see is 3 and 2 are factors of this leading coefficient, 6. So notice the denominators, zeros, the factors of the denominators come from the factors of the leading coefficient. And then look at the top, -7 and 5, -7 and 5, 7 and 5, 7 and 5. Those are factors of the constant. And that's true. Anytime an answer can be written as a fraction, say possible rational zeros, a rational number is a number that's a ratio of integers. Possible rational zeros are integer factors of the constant divided by integer factors of the leading coefficient. That's always true. And so if there are rational numbers as possible zeros, it has to fit this pattern here. This gives you a way to kind of start for some problems here. This is something you may not have ever realized, but I think if you kind of go back and you look at problems you've done of this type, you'll notice this is always true. Anytime you get a fractional answer, the top number of that fraction had to be something that went into the constant, and the bottom number of that fraction had to be something that went into the leading coefficient. It always fits that pattern. Even when it comes out to be a whole number, you can always think of, this first one, 1 goes into 6, so, even if you got a whole number, it would still be over 1. It fits that pattern. So if it can be written as a fraction, this statement has to be true. It has to have an integer factor of the constant for the numerator and an integer factor of the leading coefficient for the denominator. What this means for us is this gives us a way to come up with some things that might work. I'm not going to go, well, all right, let me go over this real quick. Let's say we were asked to divide here, and we want to divide, x squared minus 7x minus 8 by x plus 1, okay? And again, one way we can divide that is we can use synthetic division. You ask yourself, what is the 0 of your divisor? And then you list the coefficients of your dividend here. So 1x squared, minus 7x, minus 8. Make sure everybody's in the right order. Bring down the first one. -1 times that is -1. Add, that's -8. -1 times -8, positive 8, is 0. Again, x squared divided by x is an x, so this is x. That must be the constant, minus 8. And then a remainder of 0 means that if you take x minus 8 times x plus 1, you get x squared minus 7x minus 8. In other words, these are the factors of this, right? So again, that's synthetic division. So we're going to use all this stuff we've done, complex numbers, to deal with problems that we can't solve other ways. So before I get into that, let's just kind of, well, I guess I'll go over it at the end. But let's say we're asked, find all the zeros and the linear factors of the following. F of x equals 2x to the fourth minus 4x to the third minus 7x squared plus 9x minus 18. So, I'm thinking, okay, I want to find the zeros. I'm going to set this equal to 0 and try to work it out. Well, 1, 2, 3, 4, 5 terms. 5 terms. How do I work with that? I can't do grouping. I need like 4 terms. Or I guess I could do it with 6. I could do like groups of 3 or groups of 2 or something. But there's nothing I can really do here. There's no GCFs. Not everybody's even. Not everybody has an X. Not really seeing anything I can do here. So what are we going to do? Well, we're going to come up with a list of things that might be answers. Right now, there's an infinite number of possible zeros here. And what we're going to do is we're going to try to reduce that infinite possibilities into some manageable list. And so we said, in order for this to be a possible rational zero, it's got to be a factor of the constant. So 18, negative 18. So, 1 goes in there, positive and negative 1 go in there, positive and negative 2 go in there, positive and negative 3 go in there, into 18 again. I'm looking at 18. 4, no, 5, no, 6, yeah, 6. And you'll notice I'm starting to work my way down. 3 times 6 is 18, so 6 times 3 is, so what matches up with 2 to make 18? That would be 9, and then 18 times 1 makes 18. So that's the numbers that could be in the numerator over the numbers that could be in the denominator. So 1 goes into 2. Again, we're looking at the leading coefficient. This 2x to the 4, 2. And 2 goes into 2, positive and negative. And so I go, okay, well, if I go through this list and make all the different combinations I can, what would I get? Well, 1 over 1 would be 1. 2 over 1 makes 2. 3 over 1 makes 3. 6 over 1 makes 6. 9 over 1 makes 9. 18 over 1 makes 18. And then I have to say, okay, well, what about 1 over 2? Well, that would make a half. 2 over 2 is a 1. We already got that. 3 over 2, that's 3 halves. 6 over 2 would be 3. We already got that. 9 over 2, 9 halves. And then 18 over 2 is 9. We already got that. So we went from an infinite number of possibilities down to 1, 2, 3, 4, 5, 6, 7, 8, 9, 18 possibilities. So you might still think that that's a lot, and it is. But, if you're thinking about compared to an infinite number, just blindly guessing, well, that makes it a little bit nicer. And so let's say x equals 1 is a 0. Then that would have to mean x minus 1 was a factor. Well, if x minus 1 is a factor, that means it would divide in evenly into this. So I could use, notice the format here, I could use synthetic division to do that, and I would use the actual 0 value in my synthetic division. So I could sit here and go, all right, boom, let me try this. Let's see if this works. 2, negative 4, negative 7, 9, negative 18. Let me double check. 4th power, 3rd power, 2nd power, 1st power, 0 power. Okay, that's everybody. And what am I looking for? I'm looking for a remainder of 0. So 2. 2 times 1 is 2. Negative 2, that's negative 2. That's negative 9. Looking good. Negative 9 is 0. Oh, no. Remember, this last number is my remainder. I didn't get a remainder of 0. That means that didn't work. So all this stuff, none of that stuff worked. So now I need to pick a new number to try. So maybe I'll try negative 1 to see if that works. So that's 2, that's negative 2, negative 6, that's 6, that's negative 1, that's 1, that's 10, No, that didn't work. So, you just keep trying until you hit something that works. Now, I'm actually going to speed this up a little bit. I try 2 or -2, and, try to see what works here. You can kind of jump around a little bit. So, like, if you got a remainder that was positive, and the next, let's say I tried 1, I got a remainder that was negative, I tried 3, I got a remainder that was positive, then that must be a 0 somewhere in between 1 and 3. Now, it might be 2, it might be 1.5, but it would give me some way to kind of narrow this in there. But for those of us with a graphing calculator, we can actually do this a little faster. We can say, well, let me graph this function. Y equals 2x to the 4th minus 4x to the 3rd minus 7x squared plus 9x minus 18. And notice these are the x-intercepts. -2, 0. I'm just going to write that down here. -2, 0. And +3, 0. And you can see, like, if I wanted to zoom out here, I can see more of the graph. I can see how it hits down here at -18 and stuff. And, explore more of it. But really what I care about here is these x-intercepts. Where are these x-intercepts at? And it looks like -2 and +3. Now, if I go back to my list here, -2, oops, sorry, -2 here, and +3 are on my list. So that does make me think that there's, remember, if you have x equals -2, or sorry, let me do that over again. Let's try that again. If you have -2, 0 is an x-intercept, right? Then that means x equals -2 is a 0, which means x plus 2 is a factor, right? So what I can do here is I can try, let's try, if I'm dividing by x plus 2, then I'm going to use the 0 value, -2 in here. Let's see if that works. -4, -8, that's +16, which is 9. That's a -18, which is -9, which is +18, which is 0. Now, let's think about what I have here. I have 2, remember we dropped 1 power, 2x cubed minus 8x squared plus 9x minus 9. Well, I still can't factor that. If I set that equal to 0, I still can't factor. Remember, I'm looking for all the zeros. So what I want to do instead of doing that, since I looked at the graph and I said this had an x-intercept at 3, 0, then x equals 3 must be a factor, and x minus 3 must be, or x equals 3 must be a 0, and x minus 3 must be a factor. So if I divide this result by x minus 3, because again, that must go into this. And if you've ever broke down a number before by dividing, you divide one number, you make it smaller, you divide by another number, make it even smaller. That's what I'm doing here, is I'm going to divide out this x minus 3, so I'm going to use the 0 value of +3. And again, I'm just looking at this part. Don't worry about the remainder. We're done with that. Bring that down to, that's 6, that's -2, that's -6, that's +3. That's +9, remainder 0, okay. And now I have 2x squared minus 2x plus 3 equals 0. And you could say, well, maybe I could factor that. But I don't think it's going to factor. One thing I will keep in mind, though, it is a quadratic. And we know we can solve any quadratic using the quadratic formula. So let's go ahead and write that. I had 2x squared minus 2x plus 3 equals 0. All right? 2x squared minus 2x plus 3. Okay. Yep. So that's a quadratic. I'm going to use the quadratic formula. X equals -b plus or minus b squared minus 4ac all over 2 times a. So what do we get? We get 2 up here plus or minus a 4 down here. We got 4 minus, what's this? 6 times 4, 24. So negative 20, well, that's 4 times 5, so 2 root 5i. So we get x equals 2 over 4 plus or minus 2 root 5 over 4i. And then these are going to reduce. So now I'm ready to kind of write these down. Let's say my zeros are x equals, and then we go back here and say, oh, you got negative 2 is a 0, and the remainder of 0 means that's a 0, which means x plus 2 is a factor, so x minus 2 is a 0, x equals 3, we got a remainder of 0, so all right. So we got x equals negative 2 is a 0, x equals 3 is a 0, x equals, and I'm going to reduce this is going to come out to be a half, plus, here the 2 and the 4 are going to reduce, so root 5 over 2i, and then x equals 1/2 minus root 5 over 2i. Now I could write this plus or minus, but I'm going to show you why I don't want to do that, because I want to know, what are the factored forms of this? And the way you can kind of get to the factored form from the 0, if you write the zeros this way, is you ask yourself, what do I get if I were to move this number, get this equal to 0? So if I add 2 here, what would I get there? And I would get x plus 2. And then if I subtract 3 from both sides, I would get x minus 3. And if I would get this equal to 0, I'd have to subtract a half from both sides, and I'd have to subtract root 5 over 2i from both sides. And I get x minus 1/2 minus root 5 over 2i. And I have to subtract a half again, but this time I would add root 5 over 2. Add root 5 over 2i. So I'd get another x minus a half, but this time it'd be plus root 5 over 2i. Now, if you look at the original problem here, 2x to the 4th, blah, 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 right? 2x to the 4th. The first term was 2x to the 4th. If I multiply first times first times first times, I'm going to get x to the 4th, but I'm not going to get 2x to the 4th, which means there has to be a multiplier of just 2 here, which makes sense. If you look at these denominators of these fractions, you see like denominators 2's. Well, if you multiply those by a 2, that's going to get rid of that. So I need this multiplier of 2 out here to make everything work out nicely. And so there. So it's complicated. Let's be clear about that. This is complicated. So let's talk about how we approach, finding zeros and factors. One thing you can do is factor directly. And if you can, great, do that. A lot of things are factorable. If you got x squared minus 9, you just say x plus 3, x minus 3. That's factored, boom. And then you can set the factors equal to 0 and solve those. So if you can do that, great. Another thing we can do is take roots. Sometimes you'll have something like x squared plus 4 equals 0, and you're like, I don't know how to factor that. Well, if I subtract 4, you get x squared equals negative 4. Take the square root, boom, boom. X equals plus or minus square root of negative 4 is, by definition, 2i. If you have that, then you can say the factors are, so these are plus or minus 3, right? The factors here are x minus 2i and x plus 2i, right? So sometimes you can take roots to find things. Quadratic formula. Sometimes you can use a quadratic formula to do things. So these are all things I can do before doing what I just did. Let's say none of that works, or it doesn't work completely, or it only gets me so far. What do I do then? I run into a brick wall. How do I handle it? I can't group it. I can't factor it. I can't take roots because there's all kinds of different terms involved. It doesn't fit the pattern of a quadratic. Can't use a quadratic formula. What do I do at that point? And so this is the process we just did. Is first thing you do is come up with some possible zeros, possible rational zeros. Now that doesn't mean you have to make out this list like I made here with, all the factors of the constant over the factors and come up with, all, 18 of these. You don't necessarily have to do that, especially if you have a graphing utility. You could go, more by the graph, but you should be thinking numbers that go into the constant divided by numbers that go in this. So if this first number, this 2x to the fourth had been like a 3x to the fourth, I would know I might be looking at thirds, possibly. That's something I should be aware of. But you come up with some ideas of what might work as answers, and then find some zeros. Find some typically real rational zeros. And what this does is it gives you a door. It gives you a foot in the door. It gets you started. You start breaking things down. Divide until you get to something you can work with. Right? So, maybe I get to something I can factor directly, or maybe I get to something I can take a root or something like we just did. I got down to something that, did some dividing, and I got down to a quadratic. Oh, I can use a quadratic formula for that. So I get down to something I can work with. And then lastly, bring it all back together. Bring the zeros and factors together. All right, so let's look at here. Okay, so let me do one more problem. Kind of put this together here. All right. So say find all the zeros. Product of linear factors. Called linear factors because x has the power of 1. And so let's say we're looking at the function x to the fifth plus 6x cubed plus 2x squared minus 27x plus 18. And again, I'm going to set this equal to 0, and I'm going to try anything I can to see if this will work. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 can't factor. No GCFs. I mean, you should look for those GCFs, but I can't do grouping. I don't really have a whole lot of chances to do a lot of other stuff, so I'm going to have to do it this long way. And again, this assignment, you're going to do this with pretty much every single problem, but we should check, because in the future you won't know what you'll need to do. So I'm thinking about what might work here as answers. And so numbers that go in 18 again, divided by 1. So it's got to be numbers that go in 18. So what I'm going to do is I'm just going to go ahead and graph this and see what the graph looks like. If you don't have a graphing calculator, just start plugging in numbers, do that synthetic division, see what works. But I'm going to go ahead and graph this. So y equals x to the fifth plus 6x to the third plus 2x squared. Notice that we don't have an x to the fourth term. That happens sometimes when you're missing a term here. Okay, so I get to this graph, and I'm looking for the x-intercepts, because where the x-intercepts are, those are where the zeros are. And so I see I have an x-intercept at -2, 0. I also have an x-intercept at 1, 0, but notice what's different about what's happening with the graph at 1, 0 than -2, 0. At -2, 0, the graph crosses over and keeps going up. But at 1, 0, the graph doesn't cross the x-axis, it turns around. What that's telling me is there's actually at least 2 zeros there. Maybe there's 4 there. But I know there's at least 2, just like there's at least 1 here, or maybe there's 3. It's an odd number, and this is an even number. So I know I have another 1, 0. And if I go back and I look at my formula, x to the 5th, it's got to be 5 altogether. So I guess I could have 3 here and 2 there, or 1 there and 4 there. Probably there's 1 and 2, and then there's 2 non-real ones that I've not seen. Or maybe I just didn't go out far enough. You know, 18 is a factor of 18, so no, it doesn't look like our graph's getting over, coming back down. So probably these are the only 3 zeros we're going to have to deal with. So let's start cranking this out. Once we have things that work, we have possible zeros here. We think x equals -2 is a 0. We think x equals 1 is a 0. We think x equals 1 again is a 0. So let's start picking one of those. Start with -2. I'm going to go through x to the 5th, x to the 4th. Again, we're missing that, so we're going to have to put a 0 there. 6, 2, -27, 18. Leave a line, bring that first one down. This is just synthetic division we're doing here. You just use these 0 values because you think about when you do the factor, you change the sign, and then when you do synthetic division, you figure out what makes it 0. So you just use the 0. You know, don't change and change and change, and so much you kind of lose track of what's going on there. -18, +36. That's a 9. -18 is a remainder of 0. Yeah, baby, that's what we're looking for. That's what we want to happen. So, all right, remainder of 0. That's supposed to be a smiley face. It kind of got mutated a little bit, but you know, it's smiley face. All right, yeah, got a remainder of 0. But again, I'm probably looking at this. This is ugly. So I'm just gonna go ahead and I'm gonna pick my next 0. So all right, we'll use that one. Let's use 1. Boom. And so I'm bringing this down. 1. That's 1, that's -1, times 1 is 9, that's 9, that's -9, which is -9, which is again a remainder of 0, and again, yeah, like that, all right. Yeah, that works. I have something here, x squared, this is x cubed, you know, think about every time I divide by one of these, I knock this power back down by 1. So the first time I divided, it went to x to the 4th, I just divided a second time, so it's x to the 3rd. Minus x squared plus 9x minus 9. Now notice 1 to -1 is the same ratio as 9 to -9. So I could do grouping if I wanted here. If you want to do that, great. So you can stop this process anytime you get to something you can work with. I have this other 0. I'm just going to go ahead and, you know, use it. But like I said, you don't have to. You can go with that. 1. So that's 1, 0. Get this out of the way. All right, so that's 0, that's 9, 1 times 9 is 9, remainder of 0, again, yeah, all right, yeah, that's what I like to see. So x squared plus 9 equals 0. I could move the 9 over. X squared equals -9, take the square root. X equals plus or minus 3i. You know, square root of -9 is plus or minus 3i. All right, so that worked. And again, if you would have factored this here, you would have gotten x squared times x minus 1 plus 9 times x minus 1. So x minus 1 times x squared plus 9. And then, whoop, there goes that one, and there is your 1. That's that one. So you get the same answer both ways. So, well, let's put everything together. Remember, that's the last step. Let's get everything buddied together. So what are my zeros? And I recommend you write this as, you know, each one separately. X equals 1, x equals 1, x equals 3i, x equals -3i. And then my factors are, and again, move that 2 over, you get x plus 2. Bring that 1 over, you get x minus 1. Bring that 1 over, another x minus 1, so I'm just going to say that's squared. Bring the 3i over, x minus 3i. Bring the 3x plus 3. And you'll notice every time you get a non-real answer, you always get its complex conjugate. Always complex. Complex conjugate, you always change the imaginary parts. So see 3i, -3i. If we jump back up here to this earlier problem we did, we got 1/2 plus square root of 5 over 2i, 1/2 minus square root of 5 over 2i. Complex conjugates. So you always get complex conjugates. Anytime you have one non-real number, you're always going to get the next non-real number. So that's how we do the fundamental theorem of algebra. It can get even uglier than this, and because of that, some people have, you think about the quadratic formula, there's people working on other formulas. I think there is a formula for x cubed. I've never worked with it. It doesn't run up that often. That it's really something most people need to know, but I know people are working on trying to get ways of dealing with even higher power things. So there we go. Fundamental theorem of algebra. Oops. That's not what I want to do. What am I doing here? Let's stop.